I provide the first overview on the seasonal forecast evaluation, a background to also prepare the field to the other speakers, Christian and Franco. So I will give a brief introduction on the probabilistic nature of a seasonal prediction and describe a set of metrics to evaluate probabilistic performance of seasonal forecast based on the joint probabilistic distribution of observed and forecast outcomes. Then I will also try to include economic value in the discussion for decision making. And then I'll try, time permitting, to prepare also the presentation by Franco and Christian, trying to talk about what's the benefit of multimodal in the assessment. Okay. Due to the chaotic nature of the equation describing the dynamics of the atmosphere, step-by-step time evolution of the atmosphere prediction is possible only for a few days, 1 or 2 weeks at the most. And so longer forecasts, such as the seasonal prediction, has to be probabilistic. And so ensemble forecasting techniques has to be used. Have a look at how fast the geopotential I diverge in the atmosphere. And on the other hand, the ocean, which shares the same chaotic behavior as the atmosphere, but with much longer time scale of development and slowness of the processes, can have an effective effect of the initialization of the ocean over the forecasting. So we can say that seasonal forecasts are boundary value problems for the atmosphere and initial value problems for the ocean, and other components such as the land or maybe also the tropical interseasonal oscillations. Yeah, very quick and abrupt on the probabilistic. Let's go to talk about the joint probabilistic distribution of observed and forecast outcomes. On a fundamental level, probabilistic verification involves investigation of the joint distribution of forecasts and observations. Okay, you can see here the joint distribution of observed and forecast outcomes that describes the overlap between observation and forecast. And after discretizing the probability forecast to finite set of values, the joint distribution can be written in the following notation. Very important for joint distribution to be tractable. We need to identify dichotomous events, yes or no events in the observation. Otherwise, it's very complicated to handle the joint distribution. Yes or no events, you can imagine, for instance, above events that are above upper tercile of the for the temperature, for instance, so that the outcome will be an yes or a no. Here you can see the joint distribution in a 2-for-2 contingency table, which the columns are for the observed outcome, yes or no observed outcome, and for the forecast of the event or not, or the event not forecasted, the second row here. So that the joint distribution is characterized by a hit when the event is observed and forecasted, or a false alarm where the event is not observed but forecasted, or a miss when it is forecasted but not observed, and correct rejection when no forecast nor observation are showing the forecast. So let's go with, with a comprehensive set of metrics to evaluate probabilistic performance of seasonal forecasts. Very fast, don't be scared. I mean, it takes some time to then digest all this, but okay. From the definition of conditional probability, there are two ways to factorize the joint distribution of forecast and observation: the calibration, refinement factorization, and the likelihood buzz rate factorization. And the terms of the two decompositions do characterize different attributes of the forecast performance. So that, for instance, here, the probability of observation given the forecast characterize reliability and resolution. The marginal probability of the forecast defines the signal, and the probability of the forecast given the observation outcomes is described by discrimination skill. The attributes of the probabilistic performance can, for the calibration, refinement, factorization, can be easily seen from the reliability diagram here. And for instance, the reliability measures somehow the vertical distance between the probability of the observation given the forecasts versus the perfect reliability line. The resolution will be a measure of the distance between no resolution, so the climatology of the observation, and the probability of observation versus the forecast, while the signal is a measure of the spread of the marginal distribution and histogram of the forecasts. Another very important attribute is the accuracy of the forecast that can be measured by the Brya score, which is the weighted sum of the error of the forecast here. And it can be shown that Brya score can be expressed as a function of the reliability, resolution, plus an uncertainty terms like this, such that we can identify in the reliability diagram no accuracy skill line, this dashed line here, that basically says that below this line is not possible to get positive accuracy skill. The other factorization, the likelihood buzz rate factorization, is comprehensively described by the discrimination attribute that can be seen in this discrimination diagram by this discrimination distance, and basically is the difference between the conditional probability, the distribution of the conditional probability of the forecast given the event versus the other distribution of the forecast given the event not happening. So, so that this distance measure the capability of the forecast to discriminate the two outcomes of the observation, basically. Okay, so let's try to also include in this discussion a bit of the economic value for decision making. At a decision making level, probability forecasts are regarded by virtue of their economic value. Notion of value is conceptually different from the notion of skill in a methodological sense. In fact, economic value cannot be assessed by analyzing methodological variable alone, whereas it also depends on the user's economic parameters. This is very important. To try to make a step in this direction, let's go back to the contingency table we were looking before, but also considering a simple cost-loss decision model. The cost-loss decision model works such that the user is basically sensitive to an adverse dichotomous event, for instance, temperature above the upper tercile of the climatological distribution. If the event happens, then the user will experience a financial loss, but the user can take a preventive measure to avoid the loss, and given the information of the forecast, at a cost, at a financial cost. In short, basically, we can easily show that the preventive action is convenient for the user if the cost is lower than the loss multiplied by the forecast probability. Very easy to show that, but we have a problem here because at the decision level, at the decision-making level, we are assuming that the probability is reliable and calibrated, so that the forecast probability is equivalent to the probability of the outcome of the event, observed event, given the forecast. And actually, this is not quite often the case. This is a reliability diagram we were looking before, and in the example, and we can see that actually the reliability in forecast is often not non-perfect and quite weak. In particular, this case is a forecast with an overconfident forecast, and so very important for the decision making is the recommendation that in order to avoid to jeopardize the value of end user decisions, calibration should be considered anytime there's any limitation in terms of reliability. This is very important point, and in showing the connection between the skill and the value. How can multimodal help on that? So let me show just one slide, and then I will close my presentation and to also facilitate the other speakers. Okay, why do we use multi-models? Well, we have seen that single models can be wrong, and even if the single model can capture the right anomalies, they tend to be overconfident. And so the multi-models can improve by combining the skill from the single models and improve the ensemble dispersion and uncertainty consideration. And so the overconfidence we were talking about just before will be improved by multi-model approach. And in previous works, and of course, also in the work we did in SECLI-FIRM, Christian and Franco will show you in the other in the following talk. The improvement of the multi-model tend to be to increase with the increase in the dependency of the single model systems and the degree of overconfidence of the contributing single models. Yeah, I want to now give the floor to Christian and Franco. Thank you so much. And I also provide a list of recommended readings related to the talk. Thank you.
Okay, so I'm going to dive a little bit more into these multi-model combinations, how they work, and also I'm going to be showing a couple of examples from the real world. So yeah, first of all, I want to dive into why are these models actually giving us something different. One should believe that they should probably be giving something quite similar, but let's look a bit into that. Secondly, I want to look into why we gain something from combining these models in a multi-model framework. And then finally, I want to show you a couple of examples from SECLI-FIRM that Andrea has already referenced a couple of times, I think, here. So the first question is, why are these models actually giving us different forecasts? One should believe that the formulas were quite similar. We do have quite a good understanding on how the atmosphere works and so on. But even though the formulas are quite similar, there are still small differences in how the models work. Some of them have different representations, small differences, I should say, representations of what happens both in the ocean and in the atmosphere. And secondly, also, one would believe that all these models, of course, have the same starting information to start from. But again, the answer is yes and no, because different models use different observational or reanalysis data set, I should say, in this case. So there are again small differences, and they can also be started on slightly different dates, giving them slightly different starting points to start from. Here I've just summed up the models that we have been using in SECLI-FIRM. So you can see there are 11 models here, and I've just summed up what atmospheric model they're using, what ocean model they're using, and also what the initialization they're using, both for the atmosphere and the ocean. So if we look here, especially on these columns here, you can see that even though there are some similarities, we can see that some models do use the same ocean models. The NEMO model here is used several times. You can also see that there are differences between what models they use, both for the atmosphere and the ocean. And the same when we look at the initialization data sets they use. ERA 5 is represented, and ERA in general is represented sometimes. But again, there are differences in what data sets they use to start their forecast with. And finally, I should also mention that each data set can also have slightly different ways of doing their individual ensemble members. Some of them use different start dates for the example members, and others use different perturbations in order to get these different outcomes. And I'm not going to jump into depth again with this. Andrea said it quite fine before, but as we all know, it's these small differences that with time can grow larger. These uncertainties can grow larger with time, and therefore give very different forecasts. So let's try something now just for fun. The ones of you that are involved in my group session later on, you'll get to see things similar to this and also get to play around with some of it. But what I've done here is I've tried to make 4 different models. I've given them real model names, so don't be confused by this. But what you see is we have the DWD, the ECMWF, the MF, and the UKMO models. For them, I've given them a forecast for each time step here, each column you see here, of some event happening. It doesn't matter what the event is. Let's say that it could be drought, for example. So the DWD says there's a 40% chance of drought in this month, and 40 in this, and 60 in this, and 0 and 0, and so on. And that's the same for each model. Also, then I've made up an observational data set here, or reanalysis data set. Again, it's just fake data, so I've given it a real name, but the data is not correct. So the ERA 5 here, which is the reanalysis data set, then confirms whether the event happened. So it's 100% when an event happened, and it's 0 when an event didn't happen. So the next step we can do now is to try to calculate the skill of these forecasts. Andrea just introduced the Brier score, and I'm just going to take it a little bit step further here and use something called the Brier skill score. So where the Brier score was somehow similar to the mean squared error for more deterministic forecasts, you can see here we have the difference between the forecast and the observation squared and taking the mean of it. The Brier skill score is just taking this in reference to some reference forecast. In this case, I've made a climate forecast here. You can see that I've said that there's always a 1/3 risk of this drought happening. So you can see that just looking, I mean, I know nothing else than what I can see from observations. I would say that there's always a 1/3 risk of this drought happening. So you can see my Brier skill score in this case is 1 minus the difference between the forecast and the reference. That means that the closer to 1 we have, the better my forecast is compared to the reference. And if it's 0, it means that there's no difference between my forecast is not giving a better skill than the just using the climate information that I have from the past. So if we first of all try to calculate this for the individual models, as you can see up in this table here in the top, you can see that the best performing of my, again, I repeat, this is just data as you saw that I have made up, but the best performing in this case was the UKMO, and the next best was the ECMWF, the Meteo France, and the DWD, as you also see in the table up here with the exact numbers. What I've done then is I've tried to say, what if we combine some of these models and see what is the actual skill of this combination? So here they're combined with an equal weight. So if one model says there's a 100% chance of an event happening, and another one says there's a 0% chance, then the outcome of that combination would be that there's a 50% chance of this happening, and so on. And here I've then tried to test all the combinations of these 4 models. So all the combinations that has 1 model you see here, and the one that has 2 models you see here, and 3 models you see here, and there's one single combination that obtains all the models. Obviously, I cannot combine 4 models in more than one way. And what's interesting to see here is that even though the UKMO is clearly the best individual, if we combine it with information for at least these 2 here that are all less skillful individually, but even though they are less skillful individually, combined, it seems that the best combination we can get, which is this point here, is still more skillful than the UKMO by itself. So we can see the DWD was not included, but it's also by itself relatively unskillful. So the question to answer is, why is this actually happening? And Andrea has already talked about it a bit, so I'm just gonna go through this a little bit fast also. But you can see if we have, for example, two model systems. Let's say that the dashed line here is one model system, and the dashed line here is one model system, and the full lines up here is another model system. And these are just 3 ensemble members from each model system. You can actually describe more or less all cases by these 3 cases that's happening here. So they have the same starting point at t0 here, and at t equals t out here, they have now got 2 different predictions. In this case here, you can see that by combining the 2 systems, we actually end up doing some error cancellation and therefore ending up at a better forecast, which is basically also the case. But it could also be that one system, for example, here, the full lines are better than the dashed lines. Which means that this model by itself would actually be better than combining these 2, but this one wouldn't. It would be worse than combining these 2. But one thing to keep in mind here is, of course, we have no idea which model is going to be best at any time. It could be that the next month the dashed lines are actually the ones down here hitting the right forecast and the other ones up here. We have to assume that we beforehand cannot say which model is performing the best. And thereby, by taking the full ensemble always, we actually do exactly what Andrea said before. We actually kind of reduce the overconfidence of these individual models, and therefore makes the forecast more reliable. And here in the third example, we have kind of the same as this one. This time, both models are just outside the real value, but it's the same principle. By combining the 2, we still get closer to the correct value down here in an average, because again, we cannot know which model is the best one in this case beforehand. So let me try to show you some examples from the real world from SECLI-FIRM that we have been working at. So in this case here, we're looking at the Brier skill score, just as we did before in the example that I had put up. This time we don't have the 11 models that I also introduced in the table at the beginning. And still, all the gray dots here are all the single combinations. So all the combinations with 1 models, with 2 models, and all the way up to the combination that contains all the 11 models. And here, as I said, we have the Brier skill score. Here we're looking at Italy, trying to forecast a season ahead. So this is a forecast for November, trying to predict the temperature in December, January, February for an upper tercile, so the upper 35% of our observations, past observations. And in this case, you can see that models in general are not very skillful. We are close to 0 here regarding the Brier skill score, which means we are not a lot better than climate. But you can still see we can combine some of the models and end up with combinations that actually perform better than any of the individual models. And actually, just in this case, taking all the models is still performing better than taking the best individual model by itself. I can also show you the same case here, just for reliability. As I mentioned before, this is the main thing that we improve by combining our models. And you can see these are the same models, the same case as before, but now it's not Brier skill score we're looking at. We're actually looking at reliability, or 1 minus reliability here, but still the higher score you have on this axis, the better you're performing. And we can see again that we improve the reliability of our forecast by combining our models. And here I just wanted to show a slightly different example. Here we are looking at Colombia. The first thing you can notice is probably that the Brier skill score out here is considerably better. It's easier to predict things in Colombia due to the fact that it's closer to the influence of the El Niño event. As Andrea showed in the slide before, the ocean evolves on a very much slower time scale than the atmosphere, and therefore it's more predictable into the future. So if you are located in a place that's close to the ocean, especially ocean that has these events such as El Niño and La Niña, then you have higher predictability in general. But one thing that's also funny to notice in this case is that the best combination that we see noted out up here of these 6 models actually is not consisting of just the 6 best models. As you can see in this case, the JMA model here is performing better than both the Meteo France and the DWD, but it's still not included in the best combination. And the Meteo France is actually also, sorry, in this case, left out. And it's simply because these models are probably not giving out a lot of new information, which means they're probably quite similar to some of the other models up here. Or I should say, they're probably not that independent in their forecast. And by not being independent in their forecast, we have less error cancellation and so on, and the overconfidence is not tackled as much. And thereby, they're simply not included in this case. So, in order to give the word on to Franco, I here want to show you my last slide. And that is, of course, to give a couple of questions here. First of all, it could be interesting, of course, to know if we could figure out what this best combination would be beforehand. Because already, as this guy is thinking, having 11 different models gives us 2,047 different combinations we need to check. So if we added more of the models that actually exist out there, I think the Australian model is soon being available in the Copernicus data store and so on, so it'll probably also be available to more people. And adding more models, of course, would give a lot of more combinations and require a lot more of calculations to be done in order to come up with an estimate of the best combination. So what we can do is to try to look at kind of what I've mentioned, the individual skill of the forecasting system themselves, how good are they, but also how independent are they from the other systems, because this independence is kind of what drives the improvement of the multi-model combinations. So yes, I think with those words, I want to give the screen to you, Franco. Thank you all very much for your attention.
Okay.
Yes.
So yeah, the final part of this talk about the MME combination and independence. So I'll first briefly review the reason why we go for multimodal ensemble, in particular the maximization of skill by using multimodal seasonal forecast, and how the MME potential benefit amplifies with the increasing independence of the contributing systems. Then we'll see where does the model independence come from. And we have two main components here. One is the processes representation and the differences in the initialization strategies. I will then introduce a metric we have derived in SECLI-FIRM to quantify the probabilistic independence of the contributing systems, which starts from the Braille score. Then we'll see some practical examples on how to use the independence information to improve the MME combination. So, well, you have already seen these slides. Just to recall, we have here two different prediction systems, one which is completely wrong, one other which is overconfidence. So we have already seen that by MME can improve by combining the skill from the single models and improve the ensemble dispersion and uncertainty consideration. We already seen that the most important thing is that we can reduce the degree of confidence by improving the forecast reliability attribute. And in this talk, in particular, we will see the advantage coming from the independence of the contributing systems. So this is a table which represents the 11 prediction systems in the SECLI-FIRM Grand Multimodal Ensemble. Here we see that we have 5 models from the European community and 6 models from the North American community plus the Japan Meteorological Agency model. Here we see that the models differ by the atmosphere, land, ocean, and sea ice components, but also from the initialization techniques. Here you can see the different colors distinguish between the European in yellow, the North American in blue, and the Japan in green. You will see that the different models tend to share some features, and you can also see that models coming from the same community tend to share more than we have by mixing models from different communities. So that's one of the contributions to independence. So let's start. This is where does model independence come from? This is to meter temperature over winter. Here we see on the map on the right the correlation differences between ECMWF and DWD. In particular, you see that over some regions of the world, ECMWF is outperforming, like here in Canada, and other regions, it is the DWD, which is performing better. If we focus in particular over Eastern European domain here, we see that looking at the scatter plot on the left, we see that the improvement in the 2-meter temperature prediction is significantly related to how the albedo is reproduced in the DWD system, which is tend to be better than ECMWF. So here we see that how actually differences in the models are related to the way they reproduce the land surface processes. This is another example. We are in summer here, and this is surface solar radiation. We are comparing ECMWF with respect to Meteor France. Again, you see this patchy map here on the right. And you see that the same scatter plot now, the surface solar radiation difference is now related somehow to the dynamics, and particular to the moisture convergence, which is reproduced differently by the two models. So processes, teleconnections, land surface processes, all contribute to model independence when we consider the multimodal. Then, okay, this is the Brahe score. We're already seeing that Brahe score can be, well, it's a measure of the overall accuracy of the forecast, and it's essentially the mean squared error of the probability forecast. You're already seeing that it's decomposed into two probabilistic main attributes: the reliability, which characterizes the correspondence of the forecast to the average observation for specific values of the predictions, and resolution, which measures the degree to which the forecast sort the corresponding conditional observations into groups different from each other. Then there's an uncertainty term, which is not affected by the forecast. Brahe score is negatively oriented. And so in order to provide a skill measure, as Christian already presented, we derive this Brahe skill score metric, which is essentially the Brahe score normalized, computed with respect to a climatological reference forecast. So giving the improvement we obtain with the forecast with respect to just using climatology. So starting from the Brahe score, we have derived a new metric to quantify the relative independence of the two prediction systems here. So you see the structure of the score is quite similar to the Brahe score, but now we are comparing two systems, 1 and 2 here. The Brahe score covariance, which is the name of this metric, is also negatively oriented, which means that it tends to be 1 when the two systems are equal, and it tends to 0 when the two systems are completely independent. Bear in mind this because it would be very important for the rest of the talk. So now here we compare how the differences in the model skill, which is the upper two panels here, relate to the differences in, well, not the differences, to the independence of the two prediction systems. So this is how we see how independence information is relevant here with the reddish parts, even over regions where we do not see actually a significant skill difference between the two models. So independence is providing an added information with respect to just the differences in skill. This is for 2 meter temperature in winter, and this other example is for surface solar radiation over the summer. And again, in particular here, we see that we have a lot of independence in the ocean part, which is related to the fact that ICMWF and Meteo France have different initialization strategies for this component. Okay, let's go on. Here we compare, on the left, we have the histogram of the single model skill. Here we have a broad domain, the whole tropics, still for 2 meter temperature. And on the right side, we see the probabilistic independence. In particular, we see here the marginal independence, which is the average independence with respect to all, which is the red, or just the EU models or non-EU models in blue. What we see here is that even models which are very similar in terms of skill can have a very different information if we look at independence. In particular, if we see here CCSM, which is an American model, it tends to be very large independent with respect to non-European systems, the other non-European systems, although if you compare just the skill, you don't see any added value. So that's, and also even the NSEP model, which is the worst model here, you see that actually is providing a lot of independence. Well, bear in mind that BS-COV is negatively oriented, so the lower here in the histogram, the larger the independence the systems have. Again, so what's behind model independence? Here we compare the two matrices here. On the left, we have the independence comparison for 2 meter temperature, and on the right, the independence in the surface albedo, whichever we have already seen that it's the most important driver for 2 meter temperature in winter. So here we see that models with a large independency in the driver, which is the albedo, have also a large independence in the target. And interestingly, here we see that by adding a model from the NMME, the NCEP, to the European systems here, and NCEP is the only non-European model in this plot, we gain a lot of independence here. So this is an example on how we can use the independency in the MME combination. We are in 1st of August start date, which is the fall precipitation forecast for Colombia. Here we see the best combination includes the Canadian model, but Canadian model is actually the worst model if you look at its single model scale. And why it is included in the best combination? Well, if you look here at the independence matrix, we see that Canadian model is actually the one which is displaying the most independence with respect to all the other models. Let's look at another example here. We are in Italy. This is a summer 2-meter temperature forecast for the upper tercile. And in this case, we see that the best combination is composed by the two best single models from EU, which in this case appear to be the UK model CMCC, plus a non-European model, which is the CCSM. Again, stressing the importance to mixing models from different communities to make the most of the independence. Let's summarize a bit the information. Here we have this scatter plot. On the y-axis, the skill of the multimodal, and on the x-axis, the independence information. So if you remember, the independence is negatively oriented. So the lowest values of independence means the highest independence. I mean, lowest values of BS-CO means larger independence. So here we see the skill is proportional to the degree of independence. We also tested the significance of the linear regression, and it is actually significant to up more than 1%. So we see how, starting from the best combination, then skill reduces where we combine models which are less independent. So in the last part of this class, I'd like to introduce another way to improve the skill, which is to use weights. We can combine the information coming from the independence and the one coming from the single model skill into a weight which is actually directly proportional to the skill of the single models. This is just a generic function. I'm not going to go through details here. And it is inversely proportional to a function of the independence. And we can just normalize. So let's see what happens here. These are the weights we obtain, and we ranked the different models here, the different domain and different variables. So you see that the skill we obtain for this region and for this variable is by using the weights is mostly quite similar to the skill we obtain with the best combination. And also we see that by weighting, we automatically select most of the models, if not all the models which are included in the best combinations, which are indicated here in red. But interestingly, we see that for some cases, we can also get better results when we use weighting with respect to the best equal weight combination. And this is an interesting case for precipitation in summer over Spain here. So let's summarize the key messages here. We are seeing that forecast skill can be maximized by combining models in the MME. The MME benefit amplifies with increased independence of the contributing system. We have also seen where does the independence come from, in particular from the way the different systems reproduce the signal coming from local remote processes and the different initialization strategies. We have seen that independence information can be quantified by using a specific metric. In this case, we have developed during this project the Braille-score covariance metric. Then we also seen that model democracy is not always the best choice. So by using weights, we can improve the forecast skill by combining skill and independence information. But I want to leave you with the most important message, which is by using independence information, it is possible to reduce the number of models and data to produce the optimized forecast. So thank you for your attention.